Hi everyone. So we're going to start a new chapter on integration. So the last chapter was pretty much all about derivatives, right? So partial derivatives, directional derivatives, all kinds of derivatives, right? So now we're doing integrals, right? Integration. And you know, it's going to work a little differently than the integrals you did in Calc 1 and 2. For one thing, let's start with the question. Suppose I know the partial derivative of a function f with respect to x. And let's say the partial of f with respect to x is 2x plus y. Okay? So if you know the derivative, can you find the original function? Can we find f as a function of x and y? Right. And if you remember in Calc 1, the answer was pretty much yes. After all, if you know the derivative, well, let's write it the usual way. F prime of x is, 3x squared. Can you find the original function f? Well, sure. You just integrate 3x squared, and you get x cubed, right? And you can check the derivative of x cubed is 3x squared. Right. Of course, what are we missing here, right? We're missing the fact that we don't know that it's just x cubed. It could be x cubed plus 2, right? It could be x cubed plus pi squared. It could be x cubed plus, 1 over e, right? So it can be x cubed plus any constant c, right? So yes, we don't know f exactly, but we do know it up to a constant, right? Up to a constant. So can we say the same thing about a function of two variables, right? Well, we can try to integrate, right, 2x plus y, right? This is the partial with respect to x, so we're going to integrate with respect to x. And you would get x squared plus x times y, right? We're treating y as if it were a constant, right? And of course, you would expect to have plus a constant here, because if you take the derivative, right, the partial derivative with respect to x, you get 0. But here's the issue, right? Suppose I were to add y squared to this. If I take the partial with respect to x now, I do get 2x plus y, right? But the partial with respect to x of y squared is 0, right? So I still get 2x plus y as the x partial of f. So it's not just adding a constant, right? It's adding any function of y, right? So this could have been y cubed. This could have been y to any power. In fact, it could be any function of y here, right? It could be, e to the sine of y squared or something, right? As long as it just depends on y, when you take the partial derivative of that, right, you just get 2x plus y, right? So this is not just a constant, it's any function of y alone. Make sense? So absolutely, if you only know the x partial derivative, right, we don't know the original function up to a constant. We only know the original function up to any function of y, which could include a constant, of course, right? Right. This g of y could be, y squared plus 2, for example. Right. So that could include a constant as well. But it could be any function of y. Right. So then the question becomes, well, suppose you know both partial derivatives, right? Maybe if you know both partial derivatives with respect to x and with respect to y. Right? So suppose the x partial is still 2x plus y, and let's say the y partial is x minus, well, let's do 3y squared to be a familiar function, right? Okay, so we already integrated the 2x plus y with respect to x, and we got x squared plus xy, right, plus some function of y. I'll call it g of y. Right? So now if the y partial is equal to x minus 3y squared, so to find the original function, I have to integrate x minus 3y squared, but now with respect to y. Right? So now we treat x as if it were a constant, and we get x times y minus y cubed. But now you should realize that you can add any function of x, right? If I added the square root of sine of, cosine of x squared of x, right? As long as it just depends on x, when you take the y partial of it, you get 0. Right? So this could be any function of x. I'll call it h of x. Right? So, yeah, I think if we put these together now, we can come up with a function of just x and y. Right? We have the x squared, we have the x times y, and then we have minus y cubed. Right? Plus any constant. Right? It's just that, the g of y would have to match with this negative y cubed. Right? So now we know what g of y is. It's just negative y cubed. Right? Likewise, we know what h of x is. H of x has to be just this function of x, right? It has to be x squared. And the xy is common to both, so that's also going to be included, right? So I think this works out, right? I think this works out. Of course, the plus c could go with, that could go either with the g or the h, because those could also could include some constant, some arbitrary constant. So yeah, now we have f, with respect to, we have f of xy, right? And it's, again, we only know it up to a constant, as we did in Calc 1 as well, right? Or Calc 2. Right? And you should check that this works, right? That this function works if we take both partial derivatives. They are functions of x and y, of course. You should get exactly what we had up here. Right? Okay, so that's a very easy check, right? The partial with respect to x is 2x plus y, right? And the partial with respect to y is going to be x minus 3y squared. So that's exactly what we started with, so we know this works. Okay. So it does look like if I give you both partial derivatives, right, you should be able to tell me what the function is, again, only up to a constant, right? Because there's still going to be an arbitrary constant there, just as there was in Calc 1. Okay. Unfortunately, that's not the case here, right? So think about this example here. Suppose I give you the x partial derivative is equal to y, and then the y partial derivative is equal to negative x. Right, so see if you can come up with a function, f of xy, that satisfies both of these partial derivatives. Got it? Yeah, I hope not, because it's impossible, right? There is no such function. So if we were to integrate, the x partial here with respect to x, we just get x times y plus some function of y. Right? And if we integrate fy with respect to y. We're just integrating negative x with respect to y. We get negative xy. And that's the problem. It's not positive xy anymore. It's negative xy plus some function of x, right? So if we match these up, the function of y here and the function of x, the only thing that's going to be true here for both of these is a constant, right? So the only thing that's both a function of x and y at the same time is a constant. However, the big problem is not the constant here, it's what this function is, right? So is it x times y? Or is it negative x times y? Right, plus a constant. Right, so just the constant here. All right, plus c. Yeah, so which is it? Because it can't be both, right? You can't have a positive and a negative at the same time. That's the issue, right? So that's what I claimed before, that there is no such function f that satisfies both of these at the same time. Okay? So even if you know both the x partial derivative and the y partial derivative, that doesn't necessarily mean you can always find the original function, right? The antiderivative, if you will. Okay. So it works in some cases, like it did in this example here. Right. Here it did work, and here was the antiderivative. Here it didn't work because there's no consistent antiderivative, right? It can't be one with a plus and one with a minus. It's got to be one or the other. So yeah. So again, just a kind of a brief introduction to integration here. This is something that will come up again in Chapter 15. So it's a little bit of a preview of Chapter 15. So keep this in mind for later. Okay, so our first sort of proper example, and this is somewhat of a review, I hope, for Calc 1 or Calc 2. We're going to integrate, right? So this is a definite integral from 0 to y of 3x squared y plus 2xy with respect to x, right? So just as we did with partial derivatives, right, we're treating y as a constant, right? And hopefully you remember when one of the limits of integration is a variable that this will be some function of y, right? This could depend on y, but we are integrating out the x. Okay, well, the integral of 3x squared is just x cubed, right, times the constant y, right, plus, and then the integral of 2x is just x squared, right, times the constant y. And by the fundamental theorem of calculus, we have to evaluate this from 0 to y. Now remember, this was an integral with respect to x, right? So these are values of x here. I should write it the proper way here, right? Yeah, so don't get confused, right? These are what we're substituting for x. So let's do the y first. This is going to be y cubed times y. Well, we know what that is, right? That's y to the fourth, right? Plus y squared times y is y cubed, right? And then minus, well, 0 times y is 0, 0 times y is 0, so you're just subtracting 0, right? So I think we get y to the fourth plus y cubed, which, as promised, is a function of y. It depends on y. And that had to happen because this, this was a definite integral where one of the limits involved y. Or they could both involve y as well. Right. Okay, so that's one example. And here's another example. Right, and this really is a Calc 1 problem. So let's go through it super quick, right? because the limits of integration are both constants, right? 1 and 2. And whether you call this variable y or x or z or w doesn't matter, right? The y is sort of a dummy variable. We're going to get a number here, right? So when we integrate y to the fourth, we get 1/5 y to the fifth plus 1/4 y to the fourth, right? We don't need a c here because we're evaluating this from y equals 1 to y equals 2. And again, it might be a good habit to start writing which variable you're talking about here, even though there's only one variable, right? So in your Calc 1 class, you probably didn't write x equals or y equals here, right? But it should help, right? So this is going to be 1/5 times 2 to the fifth plus 1/4 times 2 to the fourth. The 4 could go on the inside or outside, doesn't matter. And then minus, right, 1/5 1 to the fifth minus 1/4, oh, sorry, plus 1/4 1 to the fourth. So what do we get? 32 over 5, right, plus 16 over 4, which is just 4, minus 1 over 5, and then minus 1 over 4, right? Okay, so we get 31 over 5, and then 16 over 4 minus 1 over 4 is 15 over 4. And this becomes 199 over 20. Right? Or if you prefer, 9.95. Not picky about that, right? So as promised, you just get a number, right? All right, so hopefully a nice review of Calc 1 problem doing definite integrals, because to be fair, you're going to be doing this a lot in this chapter. This by now should be second nature to you. So now what I want to do is sort of combine these last two examples here into one problem, right? Notice that this in here, this expression y to the fourth plus y cubed, was the result of the first integral here, right? So what I could do is I can replace the y to the fourth plus y cubed as this integral, right? Because this integral here was just, it ended up being y to the fourth plus y cubed, right? So I can write this all at once. This will be example 5 now. So we're doing the integral from 1 to 2, the definite integral from 1 to 2 of, well, instead of y to the fourth plus y cubed, it's going to be the integral, the definite integral from 0 to y of, I forgot, 3x squared y plus 2xy, right? Right. And this first integral was with respect to x, right? And then this outside integral was with respect to y. Okay? So this is what's referred to as an iterated integral. Right? You're simply doing one integral, in this case the inside integral first. You start on the inside, you do this integral, and then you do the outside integral. Right? So iterated, right? One after the other. Right? So even though this looks a little complicated, it's two integrals, right? You're not doing them both at once, right? You're just doing one and then the other, right? So the way to proceed here, right? Leave the outside integral first, and let's just calculate this inside integral. Yet again. Right. In fact, we don't have to. We did it already. That was example 3 here. And we got y to the fourth plus y cubed. So we haven't done the integral from 1 to 2 yet, right? We just get y to the fourth plus y cubed, right? And then this integral is with respect to y. So now we have to do the outside integral. And again, we did that already too. That was example 4. And we have our answer, 199 over 20, or 9.95, whichever you prefer. Right. So when you do an iterated integral, you do get a number. And what that number means, I think we'll talk about that in the next section, in the next video. For now, just suffice it to say you should get a number if this is done correctly, right? So, yeah, so the one thing you cannot do here is switch the order. If you just write the outer integral here, right, and then the inner integral, the inside integral, you don't get the same thing, right? If you try to do this first and then this. For one thing, in the end, this should not be a number anymore. It's going to be a function of y. So this will be some function involving y. Okay. So yeah, you cannot just switch the order indiscriminately like this. We have to be a little more careful if we want to switch the order. We are going to switch the order, right? I mean, in this example here, we did dx first and then dy. In other examples, you could do dy and then dx. And in fact, I think what I might do is explain what this number represents already. So this will be a little preview for the next section, but then when you get to the next section, it'll make perfect sense. Okay, so treating this integrand here as a function of two variables, right, 3x squared y plus 2xy. We can think of this as we did in chapter 13. This is a surface in space, right, sitting above the xy plane. So here's our little graph. So this will be the x-axis, this will be the y-axis, this will be the z-axis, and the graph will be some surface in space. I'm not going to try to graph it accurately. Suffice it to say, it's just some surface sitting in space, right? So this is some function of x and y. Not necessarily this function, but just some function, right? Okay. Now, the inside integral, right, notice is with respect to x. So the 0 and the y are values of x. So what's x equals 0? X equals 0 is the y-axis, right? This is the line, or in this case the plane, x equals 0, right? And the upper limit of integration is x equals y. So what's x equals y? X equals y is the same as y equals x. So that line looks something like this, right? Yeah, if I graphed it this way, right, it's just your 45-degree angle here. Let's try 45 degrees, right? Y equals x. So I'm just graphing it in the xy plane over here, right? Okay. Now, what about y? What's y doing? So with respect to y, that's the outside. This is y equals 1 to y equals 2. So y equals 1, let's say this is 1, is this line here. Right? And y equals 2 is this line here. It's a little sloppy, but pretend it's a line, right? So this defines a region in the xy plane. And if I can do it, I guess I'll do it in purple here. It's this region in here. Okay. Again, if it's a little tricky to see that, maybe let's just draw the xy plane in 2 dimensions here. Okay, so here's 1, 2, 3, and so on. 1, 2, 3, 4, and so on. All right. Yeah, and let's graph the line x equals 0. Okay. And x equals y. I know that's not very straight. I'm still trying to get used to this. Okay, that's the best I can do, right? So x equals 0 and x equals y, or y equals x, right? And then we had, right, the y's, y equals 1 to y equals 2. So here's y equals 1. I think I missed by a little bit. All right, so this is the line y equals 1, and this is the line y equals 2, right? So we're between y equals 1 and y equals 2, and we're between x equals 0 and x equals y, right? So what is the bounded region between those two lines here? And that's this region in here. Right. So that's the two-dimensional version of this region here, right? So it's the same region. The one on top here is a little bit skewed. Okay. Makes sense? Oh, I didn't want to draw the arrows, so... Okay. So there's the region again. All right, so what does this have to do with this number, this 9.95, right? That was the result of the iterated integral. Okay, so remember there's a surface sitting above this region here, right? And this surface is in green up here. And I don't know, right? It's just some curved surface like this. These are the isobars or isoclines here. So now think of the vertical column above this trapezoid. This little region is a trapezoid here. And just go right up to the surface. And you can see what happens is on the surface we don't exactly get a trapezoid. It's now a curved region here. Right? So think of this as sort of like a cap here, a little bit of a curved region, right? But underneath that surface is this sort of rectangular solid. It's like a box, except the top of the box is like curved, right? It's a curved top here. So yeah, this here gives you a volume. If we were to measure that volume, we would get 9.95. So this number, right, is the volume of this region here, this solid region underneath the surface. Okay? Right, and that should not be a surprise. After all, in Calc 1, going back to Calc 1 again, if you have a function, y equals f of x, this is going to be very sloppy here, right? If this is our function, f of x, and we have a region, in this case, just from a to b here, right? Got to close it off. And you want to find the area of that region. What would you do? You would do an integral, right? So this area in here would just be the definite integral from a to b of your function f. And that's how it was in one dimension, right? Or, you know, a one-dimensional integral. But now we have, right, a two-dimensional surface, and we want to integrate this function here to find the volume of that region underneath. Instead of underneath the curve, it's underneath the surface. Okay, so if you want to calculate the volume of that region, of the trapezoidal solid here, I'll just call it R. Actually, I'll call it Q. So this space in here is all Q. That volume is just the iterated integral. Oops, we're not doing double integrals yet. Iterated integral from y equals 1 to y equals 2 of the integral from x equals 0 to x equals y of the function. In fact, I'm not going to copy down the function. It's just a function of x and y, right? And this is dx dy. Okay. So yeah, if you measure that volume, you get 199 over 20, or 9.95. So that's just the three-dimensional analog of the two-dimensional area that you did in Calc 1. Okay, so now you know what that number means, right? Now you know what that number means. Okay, so now that I see the region, I think converting this to the other iterated integral might be a little complicated. So maybe we can do that one later. Maybe we'll come back to that later. On second thought, we better do this now, because I'll probably forget to do it later. I know I've done that before, where I said, oh yeah, we'll do that later, and then I just never come back to it. So here's the idea, right? This region R here, yeah, forget the one-dimensional, right? We're doing the two-dimensional one. So this is the region R here, right? It's the region in the xy plane. Right, so how would we describe that region? Well, we can say it's the set of all points, x, y, so the region R, x and y, such that, y is between 1 and 2, right? So y varies between 1 and 2. And x, well, x varies between 0 and y. Right, so x is between 0 and y. Again, how do I know that? Right, we're starting here at x equals 0, and we end up at x equals y over here. Okay, so going left to right. Right. Now, of course, if y were negative, we'd be going right to left. So you have to be aware of that you might get that negative part over there. But because y is positive, right, from 1 to 2 is positive, yeah, we get this situation here. Right. Of course, we can describe this in another way. It's also the set of points x, y, such that, right, y goes from 1 to 2, of course, right? But only when x is between 0 and 1. So we're going to divide this up into two parts, right? This green square over here, this green square is just, right, x goes from 0 to 1, and y goes from 1 to 2. Yep. And x is only going from 0 to 1 here, right? Right. However, then there's also this, and why don't I call this yellow here? This looks like a triangle, right? It's a triangle. So what is this yellow triangle then? It's the set of points x, y, and I feel like I'm going to run out of space here, but I'll try to squeeze it in. It's the set of points x, y such that y goes from y goes from x, which is the lower boundary here, right, to the line y equals 2. Right. So we're going from y equals x, right, to y equals 2. Makes sense? You're going from the line here. I can't use yellow, right? You're going from the line y equals x to the line y equals 2. See that? And what is x doing? X is just going from 1 to 2 now. So x is between 1 and 2, and I think I just squeezed it in there, right? So yeah, you have to take the union of those two regions, right? So they're two separate regions, and we have to describe them separately here. Right. So the purpose of doing this now is to try to reverse the integral, right? We had the integral here. Right, so this was originally the integral from 1 to 2, and then from 0 to y of some function with respect to x, then with respect to y. Right. But now we can rewrite this, right? We can rewrite the same integrand, the same surface, but we want to switch the integration from dx dy to dy dx. Right? So that means we have to interchange the limits here, right? So what is y doing, right? Y is going from 1 to 2. So let's start with the green region here, the green square. Right, y is going from 1 to 2, and x is going from 0 to 1. Right. Right. And then plus, we're going to add to that the yellow rectangle, the yellow triangle here. It's a triangle, right? So now what is y doing? Y is going from x to 2, and x is still going from 1 to 2. Okay, so yeah, so what made this a little more complicated is that we had to divide it up into 2 regions and then just integrate over each region separately. But you end up with the same thing as this, right? As long as you add the 2 together here. So that's a plus. Okay. Right. Again, go through this carefully because this is not obvious, right? And the key thing to remember here is that when you switch the order of integration, and of course I forgot the dy comes second. Oh no, the dy comes first. Yeah, so this is dy here, then dx. Oops. Okay, but there we go. Now we get the same thing. Right? So this equals this. Right. And if you didn't follow that, don't worry. We're gonna do more of these. I just wanted to make sure we did this one before we do, and I'll try to make the next one an easier one. Okay. So here's another example. We want to find the area of the bounded region R, that's the set of points xy in the xy plane, such that 1/3 x is less than or equal to y, and y is less than or equal to square root of x. Okay, so this is something you should have done in Calc 1, or probably Calc 2, but one or the other. Probably Calc 2. I don't do this in Calc 1, right? Because this is the area between 2 curves. So first thing we should probably do is figure out what that region is and what it looks like. So just draw the xy plane. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 1, 2, 3, 4, 5. Okay. So let's start with the lower boundary here, right? The lower boundary is y equals 1/3 x. Or if you prefer, x equals 3y, either way. So just draw that line, right? It's just a straight line. Or I'll try to make it straight. Right. There we go, right? So this is just y equals 1/3 x. And then the upper boundary here is y equals the square root of x. Or, if you prefer, right, x equals y squared. Right. And I think you know what that looks like. So 0, 0, 1, 1, 4, 2, and then 9, 3. Right. And then this is where they cross, right? Oh, so, well, yeah, so there's a difference between y equals square root of x and x equals y squared. Right. So we should mention that this is for y greater than or equal to 0. Because, of course, this would give you x equals y squared. But we're looking for the bounded region here, right? The region between these 2 curves. And it's a very narrow, thin slice here, but here it is, right? This is the area we're looking for. Okay. So we want the area of this region here. So first thing we have to do is find the right, the a and the b, the lower bound here and the upper bound here, right? Because we're just going to do an integral from a to b, just like you did in Calc 1, right? Right. So how do we find those? Well, from the graph it should be clear, right, that this is just 3, 9, and this is the origin 0, 0. Of course, if you didn't know that, you can solve, right, for where these curves intersect. So you just set 1/3 x equals to the square root of x, and you solve that equation, square both sides. Oops, when you square 3, you get 9. And this has two solutions, right? This has x equals 0 and x equals 9. So clearly, a is 0, b is 9. Right. And what are we integrating? The top curve minus the bottom curve. The top curve being the square root of x, the bottom curve being 1/3 x. Okay. So that will be the area. And let's just do it, right? So this is going to be 2/3 x to the 3/2 minus 2/3 x squared, plugging in the 0 and the 9. Square root of 9 is 3. 27 over 3 is 9. So I think we just get 18 minus 81 over 3 is 27. And 27... Yeah, hang on. I'm doing this just way too fast here. All right, so 9 to the 3/2, right? Square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9. 9 times 2 is 18. Oh, that is right. But we shouldn't get a negative number here, so yeah, it's not 2/3. It's 1/2 times 1/3. This should be 1/6 here. All right, so there's my mistake, right? This should be 1/6. Yep. Little things like that can really throw you off here. All right, so now this is 81 over 6, or 27 over 2. So 18 times 2, 36, minus 27 over 2. So we get 9 over 2, right? 4.5. So that's the area of this little purple region here, right? Again, nothing you haven't done before. What we're going to do now, though, is think of the area as an iterated integral. Right? And here's what I mean by that. We're going to think about this here as being the definite integral of 1 with respect to y, right? Where the lower boundary is y equals, oops, sorry, got it backwards. 1/3 x is the lower boundary, and y equals the square root of x is the upper boundary. And if we do that, now the area becomes an iterated integral. The outside integral is still from 0 to 9, right? The inside integral is now going to be 1/3 x to the square root of x. And we're just integrating the number 1. First with respect to y, then with respect to x. And if we do that, we should get the exact same thing. In fact, we did it already. We just did not think of this inside integral here as an integral of 1, right? We just thought of it as the top curve minus the bottom curve. But that's what you get when you integrate this, right? When you integrate 1, oh, let's do it, right? What do you get? You get y. But y is evaluated between 1/3 x and the square root of x. So we would write that out as the square root of x minus 1/3 x. And then you would integrate with respect to x. And that's the integral we just did, right? This is from 0 to 9. We did that integral just now, and we got 9 over 2, or 4.5. Okay. So that's the idea here, right? We can think of the area in general now as, right, so the area of region R, and let's define this more generally. The region R is the set of points x, y, such that y is between two functions, right? Maybe we should just call them g and h. Right? And then x goes between two values, a and b. X is between a and b, right? In this example, that was the 0 and the 9. Okay, so this region looks like this. So we have g of x is the top curve, h of x is the bottom curve, and let's say this is x equals a, and let's say this is, try to draw a vertical line here, this is x equals b. The region R here is this purple region in here, right? And so to get the area of that, so the area is going to be the definite integral from x equals a to x equals b of the definite integral from g of x to h of x of the number 1, first with respect to y, then with respect to x. Okay, so this is an iterated integral, right? You got to do the inside one first, and then the outside one. Right? And just to show you that you recover what you did in Calc 1, right? This is just the definite integral from a to b of the top curve, no, that's, okay, so I flipped g and h. So, yeah, g is the bottom curve, not the top curve. So this should be the h, this should be the g. Right? Because if you reverse them, you'll just get a negative. And we don't want the area to be negative, right? So h goes on top, g goes on the bottom. So yeah, so it is h of x minus g of x. Right. And this is what you did in Calc 1. Got it? Of course, you might have another region. So we want the area of another region. I'll also call it R. But now, your region is given as a set of points such that, let's say y goes from C to D, and x goes from, say, a function of y, so g of y, to h of y. Right? So what would that look like? So now a function of y might look like this curve here, right? So this is my g of y here, and then this might be my h of y here. Right? And y goes from, let's say, y equals c to y equals d. Right? So this is c, this is d here. Right? So now my region, the purple region in here is this. Okay, so I can calculate the area of that region as the definite integral from c to d of the definite integral from g of y to h of y of the number 1, but now it's first with respect to x, then with respect to y. And this is very much like the first example we did, right? And if you do it using Calc 1, although you're probably not going to see this in Calc 1 because it's top minus bottom, but here it's right minus left. Right? The right curve is h of y, the left curve is g of y, and it's with respect to y now, right? So that's having done the inside integral, right, which is just this here, right? Just like it was in this case here, right? So two options here. And again, we can do either, or we can do both, but in some cases it's more practical, like in the first case up here, it's more practical to use, if you remember the Riemann sums here, we used vertical rectangles here as the approximate area, right? So this is called a region, right? When you have vertical rectangles like this, it's a vertically simple region. So this is vertically simple. Right. In the second example, you have to be careful because, yep, you can do vertical rectangles here. That's not a problem. But what happens when you get way over here? Now your vertical rectangles will be kind of mixed up here. So you don't want to use vertical rectangles here. You want to use horizontal ones. Right? You want these to be your rectangles. So I kind of overshot here, but pretend these are rectangles, right? So this region is horizontally simple because we're using horizontal rectangles. Right. So in some cases, right, the region is both vertically simple and horizontally simple. Imagine if you just have a rectangle. Then obviously you can use vertical rectangles, or you can use horizontal rectangles, and it's both, right? For the first example we did, if you remember, it was a trapezoid, right? It was this object here. And the first way we did it using horizontal rectangles, so we did it as a horizontally simple region, right? And remember, we only needed one integral to do that, one iterated integral. Then, when we did it the other way, we did it using vertically simple rectangles. However, these vertical rectangles here are going to be different than these. So that's why we had to cut this up into two regions, right? One was a green region, and the other was the yellow region over here. So the green is the square, the yellow is the triangle. So if you go back to that example, now it should make sense, right? The horizontally simple, this is a horizontally simple region, but if you want to use a vertically simple region, you have to divide it up into two separate regions. One is a square, one's a triangle. Okay, so I hope that helps. So this example up here, right, we did this, let's see, we did dy then dx, so we used a vertically simple region. We used vertical rectangles here. Very, very short ones, but they're rectangles. But we could have just as well thought of this as a horizontally simple region. Okay, so to do that, I'm going to have to copy this down. Okay, so here we go again. Same example. And, oh, I should probably copy the graph too. Or I'll just redo it. It's fine. Just trying to pick the right colors here. So here's the y-axis, here's the x-axis. We know we're going to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. We're going up 1, 2, 3. So the square root of x was the top curve. That was the purple curve. Okay, I guess I'll use blue this time then. Okay, so that was the square root of x. And then the bottom curve, I think I used yellow, so I'll still use yellow for that, is just the line y equals 1/3 x. And this one is looking a little bit better here. 6, 2, yep. Okay. So what looked, I think I distorted it last time, it just looked weird. But now it looks a little more normal. So we're looking for the area of this region here, right? And originally we used vertically simple, we thought of this as a vertically simple region, so we use vertical rectangles. Now let's see if we can do this using horizontal rectangles, like this, right? Okay, so you don't have to, but I find it helpful to rewrite the region then. Instead of thinking about this in terms of y, think of it in terms of x. What is x doing? Right? X is going left to right, right? So we're starting on this curve, which is y equals square root of x. But notice you can't do square root of x is less than or equal to x. Right? So if we rewrite this curve, y equals square root of x, and just solve for x, we get x equals y squared. So we're going from y equals x squared, or sorry, x equals y squared, right, to the line, and this line here is what? Y equals 1/3 x. But again, we can't write it as x is less than or equal to 1/3 x. So we just have to find the inverse, right? What's the inverse of 1/3 x? If we solve for x, we get x equals 3y. So there we go, right? And even though we didn't write the bounds here, right, what is y doing? It's just going from 0 to 3. Right. And again, I didn't write the bounds for the first region here, or for the first representation of the region. And I didn't want to do that because I wanted you to find the bounds for x. X goes from 0 to 9. Remember how we found those? We had to set the two equations equal to each other up here, and we had to solve for x. So likewise, you can solve for y by setting y squared equals to 3y, and that gives you the two solutions, y equals 0 and 3. So that's where these come from, right? Okay. So having done this, now we can find the area of the region as an iterated integral. Right? The outside is going to be the dy now, and the inside will be the dx, and we're just going to integrate 1. Right, so what is y doing? Y is going from 0 to 3. And what is x doing? It's going from y squared to 3y. And that should give you the same area as before. Yeah, this one up here. 9/2, right? So if you don't believe me, let's work it out. Right? Let's do the inside integral first. We'll leave the outside integral for later. When you integrate 1 with respect to x, right, antiderivative of 1 is just x, evaluated between y squared and 3y. So that's just going to be 3y minus y squared with respect to y. And now this is just an ordinary Calc 1 definite integral, right? When you integrate 3y, you get 3/2 y squared. When you integrate y squared, you get 1/3 y cubed. And now just plug in the 0 and the 3 here. So I hope I did that right. I know I had a little trouble last time, so I hope I can make up for that here. So 3/2 times 3 squared, right, minus 1/3 times 3 cubed. And we know when we plug in 0, right, we just get 0. So this is going to be 27/2 minus 27/3, which is 9. So 27/2 minus 18/2 is 9/2, or 4.5. What does that number represent? It represents this, the area of this purple region here. So the area of that region is still 4.5, as it was when we did it this way. Okay. So we just did it by thinking of this as a horizontally simple region instead of a vertically simple region, right? Because in this case it's both. And when it's both, you can very easily switch the order of the integral. The first case we did dy, oops, sorry, where is it? Yeah, dy and then dx. Right? So whichever comes first, that's the simple. Y comes first, y is vertical, so it's vertically simple. In this example here, sorry, the x came first, x is horizontal, so that's a horizontally simple region. Make sense? Yep. Okay. Anticipating, some of you are probably wondering, where did I get 1 from? Why are we integrating 1? Well, remember 1 is our function of x and y. It's just 1 in this case. So what does that mean? It means that the surface sitting above this region is just the plane z equals 1. And if it helps, let's try to draw that region. So I'm going to try to draw it this way. It's going to be a big X here, and then Y, and then Z. So can I replicate this region here? Not easily. So we have a line, Y equals, it looks like it's coming out. So it's probably more like this. And then the curve, y equals x squared, looks like this. Sorry, y equals square root of x. Looks like this. And this is y equals 1/3 x. So maybe the orientation isn't right. Maybe it would have been better to do it the other way here, because it just looks too distorted. Okay, so here's my x-axis. Here's my y-axis. And if I can draw a vertical z-axis, that's this. Okay, so I'm going to stretch out x a little further here. All right, so we have the line y equals 1/3 x, and then we have the curve y equals square root of x. And then this purple region in here is the region whose area is 4.5. Okay, so again, that doesn't answer the question, where's the 1 come from? So think about the plane z equals 1. So here's z equals 1, sitting right above, right above this region here. Okay, so it's 1 step up above from the xy plane. Okay. Now, think about the solid region, that if you reproduce this above here, you get, that should be straight, try to make it straight. Yep. It should be this. Okay. So what we have up here is the same, same region, just lifted up one unit. Right. So what we're getting here, what we're actually calculating, I called it area, but it's really a volume. It's really the volume of this solid region between the xy plane and then z equals 1 up here. Okay. But the volume is the same as the area. The volume is 4.5 and the area is 4.5. Okay? So I hope that helps, explain where the 1 comes from. The 1 is just the plane z equals 1. But when you're integrating 1, you're just getting the volume, which if you flatten it out is the same as the area. And if that's still not clear, just think about this problem here. The definite integral from a to b of 1 dx. What is that? Well, it's the area of the region between x equals a and x equals b of the function 1. Y equals 1 is a horizontal line. And that gives you the area of this region. So, yeah, let's do it. When you integrate 1, you just get x. Evaluated between a and b, you just get b minus a. That's the area of this region. Right? Well, what else is b minus a? B minus a is also the length, the distance between b and a. Right? So which is it? Is it the length between a and b, or is it the area of the rectangle? Well, when the height of the rectangle is 1, right, the length, b minus a, times 1, is still b minus a. Here we're thinking of it as an area. Here we're thinking of it as a length. So back to this problem, yz equals 1, right? So we're thinking about the region here, the region R, the area of that region, right? Or the volume when the height is 1. Same thing. Okay, so yeah, think about that for a bit. Think of it in terms of what you did in Calc 1, where we called this the area, but it's really just the length of the interval from a to b. So now we're thinking about this as the volume underneath the plane z equals 1, but it's also the area of the region, right? Okay. Okay, so you're going to get several problems like this in the homework, where you want to sketch the region and switch the order of integration. Right? So right now the order of integration is dx dy. So what we want to do is switch it. Again, we don't care what the integrand is. It's just some surface in space, right? And we want to switch the order from dx dy to dy dx. Okay. So the hard part is figuring out the limits of integration here, because as we saw earlier, it doesn't make any sense just to switch the limits around, because you're not going to get a number anymore, right? So yeah, that is a big mistake. Don't get out of that habit here. So how do we determine the limits of integration? Well, they're giving us a big hint, right? Sketch the region. So yeah, without sketching it, it becomes much more difficult, right? Right, and you're just sketching the region in the plane. You're not trying to graph the function, right, above the above the xy plane, right? So there's the z-axis is coming out at you, but we don't really care about that, right? Right. So again, I'm going to go through this carefully again, because this is again new to most of you. So remember, the first integral here, the inside integral, is with respect to x. So these are values of x, right? So we're going from x equals 0. X equals 0 is, again, the y-axis. And x equals the square root of 9 minus y squared. You know what that is. Or maybe you don't. Well, here's a hint. Square both sides. And then add the y squared to both sides. X squared plus y squared equals 9. So that's nothing more than a circle of radius 3. 1, 2, 3. Okay, that does not look like a circle, but I'm doing the best I can. All right, so yeah, it's not an ellipse. It's supposed to be a circle, right? Okay. Oh, you might say, why, if it's the whole circle, why am I not graphing the left part of it here? So think about the square root. The square root is positive, right? Or at least non-negative. But that's x. X is going to be positive here, right? So if you wanted the full circle, then you're going to also have to tell me that x is going to be negative square root of 9 minus y squared. And we're not going from negative square root of 9 minus y squared. We're going from 0. Right? In other words, we're going from the y-axis to the circle here, left to right. Okay? Right? It's a horizontally simple region, right? Because the x comes first. Horizontally simple. Good. And what is x doing? What is y doing? Y is going from negative 3 to 3. Right? So if y is going from negative 3 to 3, then we want essentially the whole thing from top to bottom, right? So the region will be this right half of the circle, if that makes sense. Right? Okay, so now we thought of this as a horizontally simple region. Can we think of it as a vertically simple region? Absolutely. Right? We have these vertical rectangles here. So to do that, I think what we'll do is we'll have to rewrite this equation here. Right? We have to solve for y. And we already did part of that, right? We wrote it as a standard equation already. But now to solve for y, we'll subtract x squared from both sides, and then take the square root. Okay. Plus or minus. Don't forget the plus or minus. Because in this case, we need both, right? The top half of the circle is the positive square root of 9 minus x squared. The bottom half of the circle is y equals negative square root of 9 minus x squared. So we do need both the plus and the minus here. Okay. In fact, those are the limits of integration now, right? So y goes from negative square root of 9 minus x squared to positive square root of 9 minus x squared. Okay. Now what's x doing? Well, the left-hand boundary here is just the y-axis. This is x equals 0, so we're starting at x equals 0. Right? And now, how far right should we go? Right, so this is where it gets tricky, because you might think, oh, we end at the circle, so I should copy down the square root of 9 minus x squared. No, because, again, you can't have a variable here in the outer integral, because then it won't be a number. Remember, we're looking for a volume here. It's got to be a number. Okay, so what I mean by what's the rightmost value of x we want. So think of it this way, right? If the rightmost value of x is just 2, we're going to cut it off here. And we're just getting this purple area in here. And we're ignoring this area in here. Okay? So we want x to start at 0 and then go to the right. So we're going to get past 1, past 2. Here we go. You can't see that, but right here is where we're going to end, at x equals 3. In fact, we can't go past 3 because, well, there's nothing there, right? So the furthest right we can go is 3. Right? But if you just wanted the area of the region, say this, right, then you might stop at x equals 2. Okay? But we want the whole thing, so we go all the way to x equals 3. So the upper limit for x is 3. There we go, right? So what we have are two ways to calculate, not the area now, but the volume underneath the function f. We can either use this integral, right, dx then dy, or we can use this integral. Right? And we know we get the same thing simply because it's the same volume, because it's over the same region. It's the same surface, F, and it's the same region in the xy plane, right? The right half of the circle. I call it a circle. I should say it's the disk, right? So this is the right half of the disk. The disk of radius 3. Sorry. So, yeah. Okay. Let's do one more. Okay. So we have the definite integral from pi over 2 to pi of the definite integral from negative x to sine x of some function f of xy with respect to y, then with respect to x, right? So it's the exact opposite of this, where we had dx dy, and we switched to dy dx. Now we have dy dx, and we're going to switch to dx dy, right? So I'm going to need more space. I just realized that. So let's do it way down here. I'm trying to write decent integral symbols here. All right, close enough. We don't care what the function is, right? We just want to switch to dx dy. Right? So again, how to do that? Let's sketch the region. Okay. So what are we doing here? What's the region? The region R is the set of points in the xy plane such that y goes from negative x to sine of x. Okay, so negative x, yeah, okay, I'll do it in green here. So y equals negative x, right? That's just this line here. Minus x, right? And it goes in both directions. All right, y equals sine of x. You should know what that looks like. It's just the sine curve, right? And it just keeps going. So they do kind of cross in some places here. So this is the graph of y equals sine of x, right? And now we're going from pi over 2 to pi. So x is going from pi over 2 right, to pi. So pi over 2 is right here. That's not clear, is it? Pi over 2. Yep. And then pi, sine of pi is 0, so that's right here. And I tried making that straight. Try one more time. Oh gosh, this is so hard to draw on this thing. I apologize, right? But these are just the vertical lines, right? X equals pi over 2 here, and x equals pi over here. So the bounded region then is going to be what? I'll try to make it a little bit darker here, right? So it's this and this. Yep. Okay. Yeah, and this is a vertically simple region because we can draw vertical rectangles very easily here. I take that back. Not very easily for me. It's much easier for me to draw horizontal ones. Okay. Yeah. Unfortunately, though, the horizontal is going to be a lot more difficult because we're going to have to divide this up into 1, 2, 3 separate regions. So we're actually going to need 3 integrals here, right? Yeah. So this is kind of a hard one. Let's do the first region, right? So region 1 is the set of points x, y, such that, right, so we're going from x to y now. So x is going from where to where, right? So you're going left to right. So you're going from x equals pi over 2, right? Yeah, x equals pi over 2 to x equals what? Well, it's not y equals sine x. X equals arc sine of y. Right? So yeah, you have to take the inverse function, inverse sine of y. Right? Yep. And what's y doing? Y goes from 0 to 1. How do I know it's 1? Well, what's the sine of pi over 2? Right, exactly, 1. Okay, so that's the first region. What about the second region? Well, the second region just looks like a square. Okay, so that should be pretty easy. X just goes from pi over 2 to pi. Again, this is pi right here, so that's where we end here, right? So again, we're going left to right. And y goes from where to where? So what's this line here? Well, this is the line y equals negative x, right? And if this is pi over 2, x equals pi over 2, then y is going to be negative pi over 2 here. So we're going from y equals negative pi over 2 to y equals 0, right? Because that's the top part of region 2 is just the x-axis. And then the third region, so this is our triangular region. We're going from y equals negative x, but that's just x equals negative y, to x equals pi. Right? And y is going from here to here, so the top one is going to be negative pi over 2. The bottom curve here, well, if it's x equals pi, y is going to be negative pi. So those are your three regions, right? Yeah, we didn't do that here, but because I thought it was a little bit easier. All right, now we can write down the integrals, right? So for the first region, I'll call this region 1, we're going from x equals, y equals, did I get this backwards here? dy dx. Yeah, so y equals, okay, so this is x equals, yeah. Yeah, no, that's right. Yeah, trying to ignore that one up there then. Okay, so x goes from pi over 2 to inverse sine of y, and y goes from 0 to 1. Right, plus, now the integral for region 2, x goes, right, so remember this is f, and we're doing dx then dy, so x goes from pi over 2 to pi, y goes from negative pi over 2 to 0, plus, and then for region 3 here, I need a little more space. For region 3, that's the triangular region. I should mention that this is a function of x and y. Sorry about that. Again, dx, dy. X is going from negative y to pi, and y is going from negative pi to negative pi over 2. So, yep, not very pleasant to switch the order of integration here because this vertically simple region is not horizontally simple, right? It's three distinct horizontally simple regions, right? The top region here is the curved region, this is the square, and then region 3 is the triangle. Okay. Anyways, that's about as bad as it would get here. But that's how you would do, something like that. And now you might be wondering, why do we need to bother switching the order of integration? Why do we have to sketch the region? What's the point of all that? So here's an example that'll best illustrate why this is an important skill. Let's suppose we want to evaluate this iterated integral, right? And this is something we've done already. Right? We've done a couple examples like this. And the idea is just evaluate the inside integral first, right? We just take one at a time. Let's do the inside integral, and then we'll worry about the dy, right? So, can we integrate from y to 1? The integrand is the sine of x squared, dx, right? Dx. So what is that? Yeah, so what could we do here, right? We can do a substitution, maybe. U is x squared. But the problem is not the 2 here, but we don't have an extra x here. So substitution's not going to work in this case, right? It would have worked perfectly if this was the integral of sine of x squared times x dx. But nope, we don't have that extra x, right? And you remember from Calc 1, of course, that you can't just multiply by x and divide by x because that's the variable. You can do that with constants, with numbers, but not with variables, not with x. Okay, well, that's a problem, right? Because now, right, so this is not just the, negative cosine of x squared plus c, because when you integrate, or when you take the derivative of this, you're going to have a chain rule with the x coming out, and we don't have that x. Okay, so maybe it's a more advanced technique, right? Maybe it's integration by parts, or maybe it's a trig substitution. It involves sine, so it's trig something. It's probably not partial fractions. So you can spend all day trying to integrate this, because the fact is, I don't know how to do it. Right? I really don't know what the answer to this is. Right? So we're stuck. Right? This really is a mystery here. Right? Okay, well, you can type this into Wolfram Alpha or your favorite computational software, right? You can do MATLAB, you can do Mathematica. But it turns out not to be that helpful. It has something to do, it gives you some function s, capital S. And all it says about that is that this is the Fresnel S function. I don't know what that is. You probably don't know what that is, so it's just some function that we don't know. So not very helpful. Not very helpful to even do that, right? So we're really sunk here, right? If we tried to do this, we're not going to get very far. We really don't know what this is. Okay? So our only choice now is to let's look at what we're trying to integrate over. What's the region here, right? We're going from x equals y. So x equals y is y equals x. Right, to x equals 1. So x equals 1 is this vertical line here, let's say. And what is y doing? Y is going from y equals 0. Y equals 0 is the x-axis, to y equals 1. Right, this is y equals 1 here. This is y equals 0. So right, so remember what we're doing now. We're going from x equals y, so we're going from right to left. We're doing this, right? So you can see the region we want is not the upper triangle here, it's the lower one. Okay, so we want this region right here, this purple region now. Yeah, so this integral is treating this as a horizontally simple region, right? Horizontal rectangles. But we tried that, and it doesn't work. So why don't we switch to vertical rectangles, right? And see if that works. Right? So in other words, switch the order. We're going from dx dy. We want to change this to... Oops, need a little more space here. Again, don't change the integrand, right? We're just changing the order. We want to go dy dx now. And this should not be hard. What is y doing? The lower boundary for y is still y equals 0. The upper boundary is this line here. This is the line y equals x. So y goes from 0 to x. And what is x doing? Well, we're starting at 0, 0, and we're ending at 1. X equals 1. So we're just going from 0 to 1. Okay. So again, if you don't follow that, then maybe write out the region as a set of points, right? So here, x is going from y to 1, and y is going from 0 to 1. But then when we switched, we have the set of points x, y, where y is going from 0 to x, and x is going from 0 to 1. Okay. So here, that's horizontally simple. Here, it's now vertically simple. Right. So having switched the integral here from dx dy to dy dx, switching the order of integration, you might wonder, well, how does that help? Because I still have to do this inside integral here, right? I still have to integrate from 0 to 1 of the integral from 0 to x of sine of x squared. And yeah, we don't know how to integrate sine of x squared. That was the issue, right? But look carefully. What's the variable we're integrating with respect to now? We're integrating with respect to y. X is a constant. So sine of x squared is a constant. We can bring that outside the integral. Right? In other words, this is just the integral from 0 to 1 of the sine of x squared. And what we're really integrating now is the integral from 0 to x of 1 dy. Right? We'll do the dx later. But this integral, I hope you can do that in your head, because I can't make it any easier than that. Okay? When you integrate 1 with respect to y, you just get y. And by the fundamental theorem of calculus, we just plug in the x and the 0 here. Okay? So that's just x minus 0. Okay? So yeah, x minus 0 or just x. Okay, so now what do we need to do? Now we integrate from 0 to 1. I know that's a sloppy 0 here, so let me fix that. Yep, we're integrating from 0 to 1, so it's just a definite integral of sine of x squared times x dx. Well, if you remember, the first thing we tried here was substitution, right? We tried to do a substitution where u was x squared. And then du, the derivative, is 2x dx. Well, guess what? We have the x now. See, by switching the order and integrating the x, right, that gives you a factor of x. We didn't have that here. Now we do. So, by substitution, we'll multiply by 2 on the inside, divide by 2 on the outside, and now we just get the integral, or 1/2 the integral, of the sine of u du. Okay. Now, what are our limits of integration? Well, 0 squared is still 0, and 1 squared is still 1. That doesn't always happen, right? But you have to be careful, because these are x's, and these are now u's. It's just a coincidence that you get the same number for the x's and u's, right? Right. Right. In other words, if I solve this equation here, x squared equals x, I get 0 and 1. So, all right, well, we still have to integrate sine, and that's negative cosine, right? And then just plug in the 0 and the 1. So we're going to get negative 1/2 cosine of u from 0 to 1. Well, that's just negative 1/2 cosine of 1 minus negative 1/2 cosine of 0. If that's confusing, what I like to do is change it to a positive 1/2. And by changing it to a positive, you flip the limits. You make it 1 to 0. right? And you get the same answer. 1/2 cosine of 0 minus 1/2 cosine of 1, which is 1/2 minus 1/2 the cosine of 1. And the cosine of 1, well, what is the cosine of 1? Hang on. Okay, so it's about 0.54. If you're getting 0.9998, remember this is not 1 degree, right? This is 1 radian. It's just a pure number, radians, right? So this is 1/2 minus 1/2 of approximately 0.5403, and so it's about 0.2298. So I guess approximately 0.23. Okay. But here's the exact value, right? In fact, maybe we should write it as 1 minus the cosine of 1 divided by 2, right? And it's a positive number. 0.23 is the approximate, right? And these are ones, not absolute value. Sorry about that. 0.23 here, right? Okay, so there we go. We took a rather impossible task. Remember, we tried to do it this way, and we got stuck. We got flummoxed. I couldn't figure it out, right? And in fact, nobody can, because there is no fundamental antiderivative of sine of x squared. All we can do is give it a name, right? We can give it a name. We just call it s of x or something, whatever capital S is. It's the Fresnel function. So, yeah, and it's not helpful just to give it a name, right? So by switching the order of integration, we were able to take this impossible thing, and we actually got a perfectly good answer to this. We got a number, right? And remember what that number is. It's the value. It's the volume underneath the surface sitting above this this triangle here. It's a triangular region, right? So yeah. So there's some surface sitting above this triangle here. Let me draw the surface. And again, I have no idea what the surface looks like. But above this triangle is some curved surface. And we're getting the volume underneath that surface, but above the triangle. Sorry, I keep calling it a rectangle. It's a triangle, right? Okay. So that's what this number is. It's the volume of that region. And so it's a small number, it's a small volume. Okay. So, yep, in this case, to evaluate this iterated integral, we didn't have a choice. We had to switch the order of integration from dx dy to dy dx. Otherwise, we were not going to make any progress on figuring out the answer here. Okay. So, yeah, there you go. And so there are other examples like that. So again, in the book, it might give you a hint, right? Evaluate the iterated integral by switching the order. Just don't get used to that, right? If you try it directly and you end up with this weird integral that you don't know how to integrate, then that should give you a clue that you need to switch the order. Okay, so there you go. That's the basics of iterated integrals and switching the order of integration.